Thank you, Mr. Chairman, for the introduction. I'm Dario Santonoscito, a PhD student from the University of Messina. And today I will talk to you about the fatigue assessment of an high-density class of polyethylene by means of energetic approach. So in this work we investigate the fatigue properties of polyethylene 100 for pressure pipe application, and we adopted in this case a full fit technique such as the infrared thermography, and we investigate the mechanical properties of the material, and we analyze the temperature trend of the specimen surface during tensile fatigue test. And in addition, we evaluate in a traditional way the fatigue properties of this material. But the real point is that the fatigue properties are of fundamental importance, but on the other hand they are extremely time consuming. So in this work the author proposed the static thermographic method as a rapid procedure to determine the fatigue limit of the materials, adopting a limited number of specimens and during monitoring the temperature during static tensile test. This work is part of the collaboration between the University of Messina and Plus Italia, a leading company in manufacturing performance fittings, especially for large application diameter. For water and gas distribution. It is important to know that for this kind of joints, that is a flange, mixed flange in steel and the stud is in polyethylene, there is not any standard that says us how to design this kind of joints. So it is important for the manufacturer to know how to model this kind of joints. Especially in this first part of our works, we are considering the material properties. The development of a thermographic method has been proposed by Risitano, I think in the late 18 years, and the important work is in La Rosa Risitano 2000, and the methodology says that if we cyclically stress the material above its fatigue limit and we monitor its superficial temperature with an infrared camera, we can distinguish three different phases. A first phase where we have an initial rapid increment, then in the second phase the temperature reaches stabilization, until in the third phase we have a very high factor temperature increment until the failure. If we stress the material below the fatigue limit, we usually don't see anything in a thermal way. The subtender area of the temperature versus number of cycles could be related to an energetic parameter phi that we can assume constant given the test frequency and the stress ratio. So generally, the higher the stress, the higher is the stabilization temperature, but on the other hand, we can assume constant the energetic parameter. So if we apply in a stepwise way a fatigue cycle, and we obtain the different stabilization temperature, and we can calculate the energetic parameter, we are able to obtain the number of cycles for the stress ratio at which the specimen, the material, will be brought if cyclically loaded at that stress ratio. So we can plot the stabilization temperature versus the versus the stress level, and we can calculate and estimate the fatigue limit as the intersection with the stress axis. In addition, we can obtain the Euler curve for the material. 10 years ago, Risitano and Risitano proposed a novel procedure to assess the fatigue limit adopting a static tensile test. During a static tensile test, the surface evolution of the temperature exceeded 3 different phases. The first phase where we have an approximately linear decrease of the temperature due to the thermoelastic effect. A second phase is where the temperature deviates from the linearity, and the third phase where the temperature experiences an high further temperature increment until the failure of the specimen. The change in the slope from the phase 1 and phase 2 could be related to a macroscopic value of the stress that introduces in the material the first plasticization. Hence, if we cyclically stress the material with this stress, the material will be broken. For this experimental campaign, we adopted an hydraulic testing machine of 25 kN and an infrared camera FLIR at 40. We adopted specimen made of polyethylene obtained by injection molded, adopting the geometry prescribed by the ISO standard. And we made 2 different campaigns. The first campaign is a static test campaign, adopting 3 specimens with a process speed of 5 mm per minute, while the second campaign is a fatigue test campaign with 8 specimens and stress level from 12 to 17 megapascal, a load ratio of 0.1 and a frequency of 5 Hz. Here we can see the different value of the mechanical properties of this material. This is the value by the manufacturer from the data sheet. Essentially, the manufacturer adopts different processed speed in order to determine the mechanical properties. So we have an high speed for assessing the yielded stress and a very low speed for the tensile modulus. So this kind of material, as we can see in the properties obtained by the authors, are extremely dependent on the applied velocity. So if we analyze the temperature trend during a static tensile test, we can clearly see a first linear decrement of the temperature, the second phase, and the third phase. If we make the linear regression of a set of points from phase 1 and phase 2 and make their intersection, we can read in the stress curve the value of the fatigue limits determined by the static thermographic method. For the 3 tests that we have performed, we obtained a value of 12 minus plus 1 megapascal. Here's the trend of the other 2 tests, where essentially they are the same trend. And finally, we performed a fatigue test campaign, and we obtained we estimate the inverse slope of the fatigue curve with the fatigue limit at 1 million cycle and we obtain a fatigue limit of 11 megapascal, and this fatigue limit falls in the is within the static thermographic method scatter band. So we can assess that the two different values of the fatigue limit assessed by traditional method and the fatigue limit assessed by the static thermographic method could be related. Finally, very close, it is important to note that with very few specimens, free specimen, and 5 minutes per test, we can obtain in a very fastest way a good estimation of the fatigue limit. Thank you for your attention.